So in this video we're going to take a look at calculating values for simple triangles. A triangle is a 2D shape that has three sides. The sum of the interior angles of a triangle is 180 degrees. So if we know at least two of the angles in the triangle, we can easily calculate the third angle, because the third angle must make the sum of all three add up to 180 degrees. There are several different types of triangle, including a right-angled, equilateral and isosceles triangle. So to calculate the missing angle. So first we know that the sum of all the angles adds up to 180 degrees. So to work out, we use this equation. Theta plus 45 plus 60 equals 180. So we rearrange this to make the subject theta. So now we've got theta equals 180 minus 45 minus 60, which is the same as 180 minus 105, which gives us 75. So this must mean the third angle equals 75 degrees. To calculate the area of a triangle. So the triangle in the diagram is half of a square. The sides of this square measure 1 metre by 1 metre. Therefore, the area of the triangle has to be half of a metre times a metre. So if 1 metre times 1 metre gives you a metre square, the area of this triangle will be half a metre square. So the area of this shape is made up from three squares, each which have an area of 1 metre squared, and a triangle that has the area of half a metre squared. So therefore the total area of this shape is going to be 3 times 1 metre squared, because you've got three squares that have the area of 1 metre squared, which is going to give you 3 metres squared, plus half a metre squared for your triangle. So the total area is 3.5 metres squared. To calculate the area of a shape like this one, we first divide it into a rectangle and a triangle. So the area of this rectangle is 2 metres by 6 metres, which gives us 12 metres squared. So the area of the triangle, we're going to calculate the area of the rectangle, imagining the triangle it is a full rectangle, not just a triangle, which is going to be 1 metre times 6 metres. And then we're going to divide that by 2, because the triangle only takes half of that area up, which is going to give us 3 metres squared. So we add these two together, meaning the total area is 15 metres squared. Similar triangles. So if two or more triangles have the same three angles, they are considered similar. The lengths of the side of these triangles can be different, although the angles will remain the same. So in the case of similar triangles, their three sides are in direct proportion. Here we have two examples of triangles that are similar. So the lengths of the sides are different, but the angles are the same on these two triangles. So angle A and angle P are the same, angle B and angle Q are the same, and angle C and angle R are the same. With similar triangles, you can determine the length of any of the unknown sides by using this ratio. So it's not always easy to spot similar triangles. See how the triangles in the image are similar but are not in the same orientation. If you look a little bit closer, triangles A and C in this image are identical, whereas B is a similar triangle. So these triangles have a ratio of 1.5 to 1, meaning that triangle B is 50% larger than A or C. Pythagoras. So a way to calculate the hypotenuse, which is the longest side of a right angle triangle. To do this, you multiply the square of the two shorter sides together to find the square of the hypotenuse. Then you find the square root of this number, and this will give you the length of the side. So the square of A plus the square of B gives you the same area as the square of C. So then you would square root this to find the length of the line C, which is A squared plus B squared equals C squared. For example, if A was 4 meters and B was 6 meters, we would do this, which is 4 squared plus 6 squared gives us 52. So the square root of 52 is 7.21 meters because 52 is C squared. And so the length of C is going to be 7.21 meters. Now you can do this calculation for any size of any right angle triangle. So these are the references that I've used again. Once again using that Mike Tooley Engineering Technologies book.